Good morning, everybody. Welcome back. Here we begin the week of February 15th, but it's not February 15th, is it? It's Tuesday, February 16th. Actually, right now it's February 10th. Waves is our topic this week. We're moving out of mechanics into the study of waves, and we'll be in waves for the foreseeable future. Learning about all sorts of things, learning about sound waves, light waves, water waves, radio waves, seismic waves. All of these are examples of different waves, but all of these waves share one very important thing, which is waves transfer energy. So this is the link between what we've just been learning about, our unit on energy, kinetic energy, and potential energy, to waves. So waves are this thing, depending on the different kind of wave, but they all carry energy in some way, shape, or form. Think about it. Think about any of these examples from the previous slide. Sound waves. What kind of energy do sound waves carry? So sound waves are pressure waves, and we're increasing and decreasing the air pressure, which requires energy to do that. And we can measure the energy of a wave. Some waves are dangerous, some waves are safe, depending on how much energy they carry. If you think about a sound wave coming from an aircraft carrier as jets are taking off, if you're not wearing ear protection, you're probably going to destroy your eardrums. That's because of the decibel level of the sound waves that are released. So types of waves here. We can classify waves into two general types: mechanical waves and electromagnetic waves. So we just talked about sound waves a second ago. Those would be considered mechanical waves. Anyone know, are they transverse or longitudinal? Maybe you can remember from a previous class. Answer, they're longitudinal. Electromagnetic waves, we're thinking more about light waves. And so we're going to get into the difference between these kinds of waves, but we need to remember that all the waves are really into two main categories. And so in this unit, we'll be focusing on mechanical waves with sound and things like that. And then we'll be moving into electromagnetic waves and studying light. And that'll lead us into a study of optics. So some of the mechanical waves, water waves, waves on a rope even, sound like I mentioned. The big idea with mechanical waves is that they have to have a substance to travel through. Cannot travel in a vacuum. So you think about that. If you're in outer space and you want to say hello to your fellow astronaut, assuming you both have your helmets off, which is probably a bad idea, you couldn't hear each other. Even if you could take your helmet off and try to talk, the mechanical waves, which are sound waves, would not travel because in a vacuum, there is no medium for the wave to transmit and carry that energy. So the vibrations are passed from molecule to molecule. And I'm not going to get too much into electromagnetic waves now because we're going to hit that again in detail. So I'm going to focus on the mechanical waves today. So if we imagine this rope here, and we can do these experiments in class. We stretch out a string, we pull it so that it's tight, and we can create what's called a pulse. And a pulse would be created by sort of flipping your wrist. And you put energy into this rope in the form of the kinetic energy, really, of the rope material is now moving, but the energy pulse travels through the medium along the rope and eventually hits the end, where some different things can happen depending on how the end is fixed. We might get a reflection, we might have the wave be absorbed. And this last picture here is showing more of a continuous oscillation instead of just an individual pulse which is sent out. Here we're sort of wagging the rope back and forth to create not just a pulse, but a wave pattern that we can see here. Other waves, waves on water. Maybe you're familiar with surfing, big waves. I know we live far from the ocean here in Helena, Montana, but some of you have probably done this sort of thing, or maybe you've even surfed a river wave. That's fun. I used to do a ton of that when I was in college. Whitewater kayaking. It's a blast. Yeah, I still do a little bit of it, but not to the extent that I used to. Back in the good old days, Mr. Lin would go over waterfalls in a kayak. But now my back is, compressed. The physics of the impact is not a great thing to think about. So, moving on and thinking more about mechanical waves, we want to talk about the anatomy of the wave. And I bet you guys are familiar with this. Let's look at the bottom wave first because this is an easier picture to understand here. So we draw this, up and down wave motion, and we can describe some of the parts of a wave. This is called a transverse wave, where the amplitude here, which is the vertical height from this midline or median, or I forget what they call this line, but the point of equilibrium, perhaps. Anyways, we draw a line that splits the wave like this, and we measure the height of the wave, and we call that the amplitude. So the transverse wave, the amplitude is perpendicular to the direction the wave is traveling. So we have to imagine this wave is traveling through space. Let's say it's traveling to the right. And if my amplitude is vertical and my wave motion is to the right, you can see how those are at a 90-degree angle. So that sort of defines what a transverse wave is. And if we compare that to a longitudinal wave, here you can sort of see the waves as compressions and rarefactions, which have an amplitude that is parallel to the direction of wave motion. So both of these waves are going to the right. And it's harder to see the wave here, but you have to imagine that this section, which is compressed, would represent maybe the crest of the wave, and the trough here would be represented by the rarefaction. And we could this would be an example of a sound wave, so the air molecules, this would be a region of high pressure, and this would be a region of low pressure. And if we measured the distance between those regions of pressure, we can establish the wavelength of the wave measured in meters. And the wavelength is a really important descriptor of the wave. It has a direct relationship to the amount of energy that the wave can carry. And that's also dictated by the amplitude of the wave. So basically the bigger the wave with amplitude, the more energy it carries. And similarly, the shorter the wavelength, the more energy it carries, which is kind of interesting. So if you think about an example of like radio waves, radio waves are really long waves. They're way stretched out. The wavelength might be meters or more. And so those waves don't carry a lot of energy. There's no fear of damage to the human body from these electromagnetic waves passing through you, which they're doing all the time. And especially now that we're all connected to the cellular world, all that information, the wireless internet, is all traveling on radio waves. So it's a good thing they don't carry a ton of energy because then they would be damaging. On the other hand, though, we can talk about waves that are shorter wavelength like UV or gamma rays. Those waves do have a lot more energy, and we want to take some precautions against exposure. So key ideas on this slide: wavelength, amplitude, crest, trough, the difference between longitudinal and transverse. I'm not making it very far through this PowerPoint here. I'm already at 10 minutes. Gotta speed up. Okay. Now we basically talked about this slide. So here's the direction of the wave. There's the wavelength for a longitudinal wave, the distance between the two compressions. And like I said earlier, the direction of the wave, the amplitude is parallel to the direction of wave motion. You can't really see the amplitude so much on here, but it can be measured. Okay, skipping this one. And this one. We'll play with these springs a little bit in class, and you'll get a sense of what a longitudinal wave looks like. I think you've done this in earth science too, when you guys learned about seismic waves. If you can think back, seismic waves have some of these properties as well, and maybe you can remember the type of wave that a P, an S, and a surface wave are. Are they longitudinal or are they transverse? Think back. Probably should pause it. Okay, here we go. Frequency. Frequency of a wave is the measurement of the number of vibrations the wave has per second. I like to think of frequency as cycles per second. And we'll do some stuff with a pendulum this week where we can easily take a look at the motion of the pendulum and calculate the period, t, right here, and the frequency of the simple harmonic motion, as that's called. And imagine if we connected a pendulum to a string, that would sort of create waves. So frequency is going to be measured in something called hertz. And the units of hertz are basically, what a hertz is 1/seconds. So frequency and period are inversely related. And so we have seconds per cycle and then cycles per second. So frequency is cycles per second and period is seconds per cycle. And those ones are easy to get confused. So I'll put out an equation sheet as I did in the last unit on energy for all of the equations you'll need for our wave unit. Wavelength is symbolized by the Greek letter lambda and is measured in meters. So from a previous slide, we actually measure the distance between the two crests of a wave. Or you can do it between two troughs as well. The velocity of a wave we want to have in meters per second. And when we think about electromagnetic waves, we're going to use this letter c, which represents the speed of light, which is 3 × 10⁸ meters per second. So those are some of the important units. And then as far as equations here, here's one of the most important equations in this entire unit, which is, I like to call it the wave equation. And so we have velocity equals frequency times wavelength here. And this is the same equation, it's just this is for an electromagnetic wave that has a fixed velocity at the speed of light, symbolized by the letter c. I have 50 seconds. Dare I move on? Nah. Why don't you guys just absorb this picture? How's that for a teaching strategy? All right, I think I'm going to call it. You guys have a wonderful day. It's been a pleasure as usual. And in the last 20 seconds, these video lectures are probably going to be coming to an end as we move to phase 2. It'll be more live lecturing. Gonna be fun, people. Can't wait. All right. See ya.